students. In this class, we are going to learn few definitions like 1 or 2 mark questions, and later we will learn an essay question. Okay. So after the elements of symmetry, I told you to draw a line there, and after that you please put the side heading space or crystal lattice. Okay. So few definitions we are going to learn, students, few 1 or 2 marks questions. Then we will learn one essay question. So first one, space lattice or crystal lattice. Space or crystal lattice. So what is meant by a crystal lattice? So we all know that the molecules in a solid, in a crystalline solid, they are arranged in a regular pattern in a 3-dimensional space. So this is what forming the crystal lattice. So how do we define a space or crystal lattice? So please write down, students, a 3-dimensional regular pattern of arrangement of constituent particles. In the brackets you mention ions or atoms or molecules. Close the brackets. In a crystal is called as crystal or space lattice. So what is it, students? A 3-dimensional regular pattern of arrangement of the molecules or ions or atoms in a crystal is called as space or crystal lattice. And continuation, students, and the positions of these particles and the positions of these constituent particles in a crystal lattice, we call them as lattice points or lattice sites. Spelling L-A-T-T-I-C. Okay. So this is what you are supposed to write when you are asked what is meant by a crystal or space lattice. So is it clear, students? Okay. It is just a 3-dimensional regular pattern of arrangement of constituent particles, and the positions of these particles we call them as lattice points or lattice sites. Next one, put the side heading unit cell. Unit cell. Students, unit cell means this is a smallest portion which on repetition forms the entire forms the crystal structure. Okay. So a smaller repeating sample or portion or unit in a crystal which represents the picture or shape of the entire crystal. Write down, students. Unit cell means the smallest repeating sample or unit or portion in a crystal which represents the picture or shape of the entire crystal. Okay. So on repetition it forms the or it gives the entire shape of the or entire picture of the crystal, students. This is what we call it as a unit cell. Clear? Next, put the side heading Bravais lattices. B-R-A-V-A-I-S. So this is the name of a person, students. He is a French crystallographer. So put the side heading Bravais lattices. Okay. So in this chapter we all know that we are studying about cubic crystal systems. So like that there will be total 7 crystal systems, students, and the crystal lattice of these 7 crystal systems can be arranged they can have 14 possible arrangements. Okay. Like cubic crystals, they can have 3 arrangements: simple cubic lattice, face-centered cubic lattice, body-centered cubic lattice. I think you must be knowing about these 3. So these possible arrangements of crystal lattice of crystal systems are called as Bravais Bravais lattices. So why this name Bravais lattices? Because this French crystallographer by name Auguste Bravais in 1848 he observed and he showed that the crystal lattice of all the 7 crystal systems can have 14 possible arrangements, out of which cubic crystals can have 3 possible arrangements. They are nothing but simple or primitive cubic lattice. Next, face-centered cubic lattice, that is FCC, and BCC, that is body-centered cubic lattice. Okay, I will read once for you students. A French crystallographer named Auguste Bravais in 1848 showed that the space or crystal lattices of all 7 crystal systems can have only 14 possible arrangements called as Bravais lattices. 14 possible arrangements, and these are called as Bravais lattices. Okay, so now you understood why these are called as Bravais lattices, because these were observed by the person or the French crystallographer by name Auguste Bravais. So after his name, these are named as Bravais lattices. Okay, and for example, crystals of cubic crystal system have 3 kinds of Bravais lattices. 3 kinds of Bravais lattices. First one, simple or primitive cubic lattice. Second one, face-centered cubic lattice and body-centered cubic lattice. Okay, completed students. I will show now these 3 arrangements. So students, draw the 3 representations. First one is simple or primitive. In this, we can observe the arrangement of the constituent particles at the corners of the cubic crystal. Second one is face-centered. The constituent particles arranged at the corners as well as center of each face of the crystal. So there are 6 faces. At the center of each face, one molecular or one constituent particle will be there. And the third one is BCC, that is body-centered cubic lattice. Along with the corners, there will be one constituent particle at the center of the crystal. So these 3 are the Bravais lattices of cubic crystal systems. Okay. So till here you were supposed to write under Bravais lattices. Next, put the subheading crystal systems. Crystal systems. So I told you there are 7 different types of crystal systems. So how this classification has been done? This is being done based on the cell parameters of a 3-dimensional the unit cell in a 3-dimensional crystal lattice. Okay, so please write down. Later I will give you the diagrammatic representation. The unit cell of a 3-dimensional crystal lattice. The unit cell of a 3-dimensional crystal lattice is characterized by dimensions, brackets, A, B and C, close the brackets, and angles, brackets, alpha, beta, gamma, close the brackets, which are called as cell parameters. Students, please underline cell parameters. Full stop. Basing on this, this means what? Cell parameters. What are cell parameters? The dimensions and angles of the unit cell in a 3-dimensional crystal lattice. What is an unit cell? It is the smallest repeating portion which represents the entire shape or picture of the crystal. Okay, so that unit cell is characterized by dimensions A, B and C, and also angles. We can name them as alpha, beta and gamma. So these are called as cell parameters. So basing on these cell parameters, the crystal systems are classified into 7 types, or it was observed that there are 7 crystal systems, out of which we know cubic crystal systems. Okay, so basing on this, there are 7 different types of crystal systems, namely, write down all the 7 names. First one, cubic crystal system, comma, tetragonal, comma, trigonal, comma, monoclinic, comma, triclinic, comma, orthorhombic, comma, hexagonal. Okay, so these are the 7 crystal systems, students. So now we will draw I will show you the diagrammatic representation. So students, please draw this diagram under crystal systems. So what did we write there? The unit cell of a 3-dimensional crystal lattice is characterized by dimensions and angles. Okay, draw the 3 axes x, y, z, mark the unit cell and the distance at which it cuts, mark along z as A, along x as B, along y as C, and inside mark the angles, students, alpha, beta and gamma. Okay, so basing on these parameters, crystal systems are of 7 types. Okay, so this you will be writing under crystal systems. Next, last one is the coordination number. Put the side heading coordination number. So what is this coordination number? You must be knowing about this, students. You must have learned in your intermediate level. So just write down the definition. The number of positive ions. The number of positive ions surrounding a central negative ion. The number of positive ions surrounding a central negative ion, in the unit cell of a crystal, is called as coordination number. Full stop. So based on this number, students, the crystals get different shapes basing on the coordination number. So if it is 2, write down, it's linear. 3, the crystal has a shape triangular. If the coordination number is 4, it has tetrahedral or square planar. And if it is 6, it will be octahedral. Okay, so this is all about the coordination number. Students, these are all the 1 mark questions in this chapter, solid state. So draw a line till here. Let's move to the next important essay question. So students, put the side heading X-ray diffraction - Bragg's equation. So do you know this Bragg's equation, students? How many of you remember the equation? Kindly raise your hands in the comment section. And how many of you are feeling happy looking at this side heading? Raise your hands in the comment section. Right. So this is a very, very important question, students. 100% for sure we can expect this question in the examinations, internal as well as the end semester exam. Okay. So almost 95% will score full marks in this answer. So ready? So we shall learn what this X-ray diffraction is and how Bragg has derived this equation. Okay, so mark it as an important question, students. X-ray diffraction, Bragg's equation. Okay, so before Bragg has performed an experiment, actually the principle was observed by another person who is from Germany, and he was a physicist in the year 1913. Max von Laue, MAXVONLAUE, students, his name. In the year 1913, he observed that there is a possibility of X-ray diffraction by the crystals. What is the meaning of diffraction, students? Bending of the light waves into dark and light colored bands. Okay, so X-rays are being diffracted when this light is being incident on a crystal. Okay, what is the reason the X-rays are being diffracted? The reason is the wavelength of X-rays and the interatomic distances in a crystal. These two are of the same order, because of which X-rays are being diffracted when they are incident on a crystal. So this was observed by the German physicist by name Max von Laue. Okay, so write down. A German physicist, Max von Laue, in 1913 suggested that there is a possibility of X-ray diffraction by crystals. X-ray diffraction by crystals, and the reason for this is the wavelength of X-rays. Wavelength of X-rays is of the same order as the interatomic distances of a crystal. Okay, full stop. So this was the principle given by this German physicist, students. Now W.H. Bragg proved this by doing the experimental part. So what and which experiment and how did he has done this experiment? Let us see now. So below write down W.H. Bragg succeeded in diffracting X-rays from NaCl crystals. Okay, so in his experiment, what did he do, students? He has taken NaCl crystals and he proved that the X-rays are being diffracted from NaCl crystals. So what exactly is happening when these X-rays are being incident on a crystal? So below he has given the explanation. So what was the explanation given by Bragg? When X-rays are being incident on a crystal, what these X-rays are doing, students? They are venturing or penetrating deep into the crystal, and after going deep into the crystal, they strike the atoms. Okay, so they strike the atoms which are arranged in successive layers in a crystal, and from each layer they will be reflected back. Okay, so this is what he has observed when X-rays are being incident on the NaCl crystal. Okay, so according to Bragg, write down this sentence mark. According to Bragg, when X-rays are incident on a crystal, they penetrate deep into the crystal. Strike the atoms arranged in successive layers, and from each of these layers X-rays are being reflected back. Okay, so this is what happening actually, students. So below write down, based on this he could derive an equation. Based on this he could derive an equation which gives the relationship between wavelength of X-rays in the brackets lambda. Based on this he derived an equation which gives the relation between wavelength of X-rays brackets lambda, comma, distance between the two successive layers in a crystal brackets small letter d, and angle of incidence brackets theta. Okay, so based on this he derived an equation which gives us the relation between lambda, small letter d and theta. Full stop. This is called as Bragg's equation. This is called as Bragg's equation. Full stop. Okay students, this is the introduction that you are supposed to write under Bragg's equation. Okay, so later we will move on to the derivation part of Bragg's equation. So now put the side heading students, derivation. Okay, so write down under this derivation, let us consider a crystal having parallel layers separated by a distance d, small letter d, separated from one another by a distance d, small letter. Okay, so below comes the diagrammatic representation. So this is the crystal in which the atoms are arranged in successive or parallel layers, students, and these layers are separated by a distance d. Okay, and take a pencil, scale, eraser. Please draw the diagram neatly, students. Just 1 minute time I will give you. Draw the diagrammatic representation of Bragg's equation. Okay, name the rays as A, B, C, and after reflecting their names D, E, F, and this point mark it as O, and mark the angles, students, theta and theta. Next, two dotted lines here, L, here this point as N, mark this point as M. So draw the diagram neatly, students. So while explaining, it will be easy for you. So after drawing, just mark the angles here also. This angle as theta and this also as theta. Okay, completed. So first what did we do? Let us consider. So we have taken a crystal in which the atoms are arranged in parallel or successive layers, and each these layers are separated from one another by a distance d. Okay, now on such crystal, when X-rays are being incident with an angle theta, okay, so X-rays are incident on the crystal at an angle theta, what happens? So some of these X-rays, you can see in the diagram, students, from here itself D has been reflected. Okay, so that's what we have mentioned here. When a beam of X-rays is being incident on a crystal at an angle theta, some of the rays will be reflected back from the upper layer itself at the same angle theta. There will be no change in the angle. Okay, angle of incidence and angle of reflection, both will be same. Okay, so sometimes what happens, some of the rays, they will be reflected back from the upper layer itself at the same angle, whereas few rays, they go deep into the crystal, they strike the atoms, and then they are reflected back from the successive layers. Okay, so till here written at the same angle theta, while some others will be absorbed and then get reflected back from the successive layers. Okay, so this is these two or three sentences, the description about the diagrammatic representation. Okay, now let us look at the derivation part. So look at the figure, students. We have marked few letters A, O, B, L, N, M, and D. Okay, we are going to concentrate on these letters. So here I have written, see students, from the figure, AO is reflected. So we have seen that X-rays are being incident on the crystal. Some of them they reflected back from the upper layer itself at the same angle. Few they were absorbed and then they were reflected back from the successive layers. Okay. Now going into the derivation. AO. Where is AO, students? Can you see AO in the diagram? The name of the first ray. Okay. This AO is reflected back from the point O. Can you see point O? Right. Along, it is reflected back along OD. Did you find OD in the figure, students? Okay, so this is the first ray AO which is reflected back along OD from the point O. Okay, next coming to the second ray. What is the name of the second ray? BN. Okay, now, so compared to AO, now BN, it has a traveled extra distance. That means it is being absorbed into the crystal. So if we compare AO and BN, BN has traveled little extra distance than AO to emerge out of the crystal. So how much extra or how much more distance it has traveled to come out of the crystal? That extra distance is represented by L and M, students. L, N, M. This is the extra distance traveled by BN when compared to AO. Okay. Now, this difference, this extra difference traveled by ray BN, we call it as path difference. So, write down, when compared to AO, BN has to travel more distance. In the brackets, mention it as L and M to emerge out of the crystal. Full stop. This difference is called as path difference, which underline, students, path difference, which is represented by capital letter F. Okay. Now, therefore, below write down, therefore, F is equal to, so the extra distance is represented by what? L and M. This L and M can be written as F is equal to Ln plus Nm. Therefore, F is equal to Ln plus Nm. Mark it as equation 1. Students, this path difference we are writing from the diagram. Okay. So, originally what path difference is? We will see now. First, you will write F is equal to Ln plus Nm. Mark it as equation number 1. Below write down, the path difference is equal to integral multiple of wavelength lambda. Path difference is equal to integral multiple of wavelength. What is the meaning of integral multiple of wavelength, students? Integer multiplied by wavelength, we take it as n into lambda. Okay. Therefore, F is equal to n lambda. From this, F is equal to n lambda. From the diagram, F is equal to Ln plus Nm. Mark this as equation 2. Okay. So, from equations 1 and 2, we can equate n lambda is equal to Ln plus Nm. Students, look at equation 1. F is equal to Ln plus Nm. Equation 2, F is equal to n lambda. Both the equations left side there is F. So, we can equate the right hand side portions. Hence, n lambda is equal to Ln plus Nm. And also look at the diagram carefully, students. There are two triangles which are similar. One is OLN and the other one is ONM. Can you see the two triangles? Yes, these two triangles are similar and hence the distance Ln and Nm will be same. These both will be same. Ln and Nm will be same because these two triangles are similar. So here write down, since triangles OLN and ONM are similar, Ln will be equal to Nm. Okay, therefore, below write down, from triangle OLN, so look at the triangle OLN sin theta will be equal to, you can write it on your own, students. Sin theta is equal to ln by ON. It is equal to ln by d. Why ON is taken as d? Why ON is taken as d? Because the distance between two layers, we considered it as small letter d. Therefore, it is equal to ln by d. Brackets you can write since ON is equal to d. Next below, from triangle ONM, sin theta is equal to nm by ON. It is equal to nm by d. So from these two students, ln is equal to sin theta into d. So ln is equal to d sin theta. Next, from here, nm is equal to d sin theta. Below write down. Therefore, ln is equal to d sin theta and nm is equal to d sin theta. Understood till here? So what we will do with these two values, ln and nm. So you can substitute in equation number 1. So students, substituting ln and nm values in equation 3 it's not equation 1. We get n lambda is equal to d sin theta plus d sin theta, which is equal to 2d sin theta. So put n lambda is equal to 2d sin theta in a box, and below write down, this is called as Bragg's equation. Below write down where n is an integer, 1, 2, 3 and so on. Lambda is the wavelength, d is the distance between two successive layers, and theta is the angle of incidence or angle of reflection. Okay, so draw a line till here, students. So this is the answer for your Bragg's equation. Okay, so this is all for today's class. So we'll meet in the next class. Take care, stay safe, and bye bye.